All right, we've talked a little bit about informal proofs. This is our first real journey into doing proper two-column proofs, which is how we'll do all of our formal proofs in geometry. We start with algebraic proofs for a few reasons. Number one, you already know algebra, you know how it works. So putting what you already know into the structure of a proof is a comfortable way to get started. They're also pretty straightforward, and then most importantly, they're the most linear proofs. So they just follow a single path of information, and each output of one step becomes exactly the input of the next step. There's no branching paths or more complex logic that goes into it. They're all really simple and straightforward. So that's our starting point. We start off with properties because a proof needs things that go into it to justify what we're doing. We saw with the informal proofs that we have the postulates about points, lines, and planes that we can use as some justifications for our arguments. In these proofs, we're going to be using the tools that you use in algebra problems, like addition, subtraction, multiplication, and so on. So the properties are called the addition property of equality. I'm going to zoom in a little more and make this a bit bigger. Addition property of equality, subtraction property of equality, multiplication property of equality, and division property of equality. So all of these are basic tools that we use, and they only work with equations. So addition POE is where we add to both sides. Subtraction POE is where we subtract from both sides. And technically, we don't really need the subtraction POE because if you're subtracting from both sides, you could just frame that as adding a negative number. But we typically, if we're doing -4 on both sides, we call that subtraction POE rather than addition POE. Multiplication is where we multiply both sides. And just as a side note on that one, like special, like star note, does not include distribution. So, for example, if I had an equation that said 1/2 x equals 2y plus 7. And I wanted to multiply both sides by 2 using the multiplication property of equality. I would then have x equals, and I would not have 4y plus 14. I would have 2 times 2y plus 7. So the multiplication property of equality says that we multiply both sides of an equation, not we multiply all the terms of an equation. So then we would have to use a separate property down here, distributive property, in order to actually distribute the 2 to the two things in the parentheses. And division is dividing both sides. Again, you would need to distribute afterwards, so it has the same asterisk. And kind of like subtraction, division is like a fake operation because dividing is just multiplying by a fraction anyways. So if we're dividing both sides by a number, we typically call it division, even though you could say we're multiplying by a half or a third or whatever fraction. The last one I have here is not a property of equality, but I'm going to put it here anyways. So we can use simplify as a reason, and we do that for several things. We do it mostly for combining like terms. We can also use it if we need a step where we simplify a fraction or radical. Typically, you don't need to take a separate step for simplifying fractions and radicals. When you divide something, you just go ahead and put it into the simplified version. So if I had like 3x equals 6, then I wouldn't write x equals 6 over 3 after using the division property of equality. I would just go straight to writing x equals 2. So if you did put that middle step in, you put x equals 6 divided by 3, then the way you would get from that to x equals 2 is by saying simplify as your justification. So those are our properties of equality. They're the things that we use when there's an equal sign, and they're our basic algebra operations. You could also have square and square root properties. Well, you can have square root property. You can't have square property. So we won't deal with algebraic proofs of quadratics, but you could have a square root property where you square root both sides. And in that one, we know from our work with quadratics that you're going to end up splitting that equation into two versions. So it gets more complicated, and that's why we're not going to mess with proofs with that. So if I had something like x squared equals, well, let's make it a little more interesting than that. So x plus 2 squared equals 16. Then I could square root both sides, but then I end up with x plus 2 equals plus or minus 4. So now I'm working towards two separate answers, and it becomes a little messier. Likewise, we don't really have a step for factoring. It would be the opposite of distribution, so it would be in this list down here that we're about to go to next. So these are our basic properties, just our operations that we can do. All right, so additional properties of equality. Distribution. So we could call this, I'm going to call it distribution rather than like distributive POE. The reason for that is distribution doesn't rely on an equal sign, it just happens on one side. So even though we're talking about solving equations, these are not necessarily all ones that need an equal sign. So distribution would be, in the example we had above, if we had, and we could actually put factor with it as well. So we'll have distribution or factor. We'll never use factoring because, again, we're not doing quadratics, but it would be the same kind of step where you either distribute or factor something from a set of, from a polynomial. So if I had x equals 2 times 2y plus 7, then after distribution, my next step would say x equals 4y plus 14. Like that. So you know what distribution is. This is just the name we give it in our proof to say that we're distributing something. And remember that it is a separate step from multiplying or dividing. It takes two steps to multiply or divide and then to distribute. Next thing we have is substitution. This is another one-sided operation, so it isn't necessarily a property of equality. It just says that we can swap something, well, we'll say substitute, can substitute something of equal value. Something of equal value. And that's the one reason I would say that I usually do call it substitution POE. But if you just call it substitution, I'm not going to like count off for that. So substitution or substitution POE, we're substituting something that's equal. So that's if I had something like, well, let's just go with what we had above. If I have x equals 4y, I hate how it draws y, is 4y plus 14. And then in a separate step, I had y equals 2. That would give me the ability to substitute the value of 2 where y is. And I could combine these two to say x equals 4 times 2 plus 14. So that's substituting, is swapping out the value of something for something else that's equal value. So that could be a variable for a constant or a variable for another variable. We're going to use this more when we get into geometry stuff than we will in algebra. Reflexive is one that at first glance seems very useless. So it's reflection property of equality because it does rely on having an equal sign. And it says that x is equal to x. Whatever the thing is equal to itself. And within the realm of algebra, this is completely meaningless and pointless and hard to see why we have it. So just as kind of like a preview for the future, if I had a drawing like this where there are two triangles and we had like A, B, C, D, we would want to have a proof that led to the conclusion that triangle ABC is congruent to triangle, what would it be, CDB? And we can do things within the proof. So there's a bunch of steps leading to maybe this is congruent to this and this is congruent to this. But one of the ways that we prove two triangles are congruent is by what we call side-side-side congruence, meaning that all three sides are congruent to each other. And if I've proven that AB is congruent to CD and AD is congruent to BC, I still need a way to say that DB is congruent to itself. So that's where the reflexive property comes in and says that dB is congruent to dB, or in this case it would be dB is equal to dB, but because we're talking about equations, but hopefully that gives you the idea that this is not as useless as it at first seems, but within doing algebraic proofs, there's no reason we would ever use this one. So it'll be useful later. Symmetric property of equality is useful, but in a way that feels really dumb. So symmetric property of equality, if you end up, when you're solving an equation in algebra, if you get something like 13 is equal to x, then we consider that finished. X is by itself, x is equal to 13. But if your proof says to prove that x equals 13, then you have to have that exact statement as the last step of your proof. And the symmetric POE lets us switch the sides and say 13 is equal to x. So it lets us switch from 13 is equal to x that we had here to x is equal to 13. So it lets us flip things around by showing us that an equation sign it works in both directions, so it's symmetric. So if I have x on the wrong side, this is the property that allows me to flip it to the correct side. And then finally, transitive, which I should do with substitution, but whatever. So transitive property of equality, it lets us chain things together. So basically the same idea as the law of syllogism. You may remember we had an example before that said something like AB is equal to CD, and CD is equal to EF. So we could conclude from that, we could say, therefore, AB is equal to EF. So the name of that property that lets us do that is called the transitive property of equality. And this one's a little tricky because it also looks a lot like the substitution property of equality. So if I think about taking CD is equal to EF. So if I substitute EF for CD, then I would end up with the same result that I just did. So if you could think of transitive as a subset of substitution. So I'm going to try to explain when we're going to use each one. Substitution is substituting one thing into an expression with multiple parts. So here, I substituted part of the right-hand side where y was. Whereas if I had x equals y and y equals 3, then when I say that x is equal to 3, I'm not substituting one thing on this side. I'm replacing the entire thing, and basically the two sides of the equation, this one and this one, are identical. It's not just a piece that we're replacing, we're chaining the entire two statements together. So think of it like taking this one and overlapping it. So we end up with x equals y equals 3, and then we take out the middle part. So that one's the toughest to explain because they're so similar, and you could always say substitution in place of transitive in theory. But if it is something where the whole statement chains together like this, then I expect you to use transitive, not substitution. So we'll do examples, and hopefully we'll see where to use each one as we go forward. Okay, two-column proofs. Two-column proofs are set up with a heading and then a vertical line like a giant T. And we have on the left statements or steps. And on the right, we have reasons or justifications. And we just start with step 1 is always whatever is given. And the final step, step X, is going to be whatever it said to prove is going to be our final statement. So we can use properties, definitions, postulates, and theorems in order to make our way through this. So each of the steps in between is going to be one of these properties that we've talked about. But we can also use definitions, postulates, and theorems. So let's go ahead and just write examples. Talking through it any more than that would be not that helpful. So we'll go ahead and just make examples instead. So for my first one, my steps and reasons. Step 1 is always for free. You just put what exactly is given. So I would put 4x minus 1 equals 27, and the reason is always given. If there's multiple pieces of given information, so here we just have this one equation. If there were multiple things that were given, you can write them all together or write each one as a separate given line. So you can put basically multiple statements, 2, 3, 4 statements, and then put given for all of those. Or you can write 1, 2, 3, 4 and write given as the reason for each of those if you want to organize it that way. Within algebraic proofs, though, we don't have to worry about that. There's always just one given information, which is our starting equation. So with step 2, let's go ahead and over here we'll solve it like algebraically. The next thing I would do is my operation would be to add 1 to both sides. Then I would rewrite this as 4x is equal to 28. So my next step is whatever my next rewritten version of the equation is. So I would put 4x equals 28. And then the reason is how we did this in-between step. So in this case, we used the addition property of equality in order to add something to both sides of our equation. The next step would be to divide both sides by 4. So in green, that's going to be our reason. And in blue, we're going to have x equals 7. Remember, we don't need to write x equals 28 over 4. We can go ahead and do that simplification because we're dividing by 4. We don't have to write it as an improper fraction. We can just put it as 7. So we end up with x equals 7. That is our proof statement, meaning that the proof is finished at this step. We just need to provide the reason that let us get there, which was the division property of equality. For example 2, we have, I'm not going to write steps and reasons at the top every time, but you know that they're there, so steps and reasons. We start off with a divided by negative 6 plus 2 is equal to 5. That's given. Step 2. The first thing I need to do is subtract 3 from both sides. So my operation is subtraction POE. And I'm going to end up with a divided by negative 6 is now equal to 3. My next step, I need to multiply both sides by -6. I do that using the multiplication, POE. And that gives me A equals -18. A equals -18 matches our proof statement, so that means that this proof is finished. So pretty easy, and just normal algebra stuff. Statements, reasons. So this one, our given information is -9, parentheses, 2x minus 3 equals 63. This is given. The first thing that we would do here, there's two options. So this is where algebra can sometimes lead us down different directions. I could and should divide both sides by -9. That would give me, would get rid of the -9 and give me equal to -7. Actually, let's just write this proof both ways. So first step here is division POE. That gives us 2x minus 3 equals -7. I divided both sides by -9, and now this is the result. The next step I need to add, so I have addition POE. So I'm going to add 3 to both sides. 2x equals -4. Step 4, I need to divide by 2. Division POE. So we end up with x equals -2, and that was our proof statement, so we finished that one. Let's look at an alternative way of doing this for those who see parentheses and your first thought is, I need to distribute. Because sometimes you do need to distribute. This case we didn't need to, but sometimes we do. So let's look at working it a different way and compare. So first step here, we're going to use the distribution property. You can put POE if you want, but again, since it's only happening on one side, it's not really a property of equality, it's just a property of expressions. So we have -18x plus 27 equals 63. My next step now would be to subtract. So this would be subtraction POE. We end up with -18x is equal to 36. Step 4 would be division. Division POE. That leaves us with x equals -2. So we ended up with the exact same number of steps, and it really made no difference whether we divide first or distribute first. Even if we did have a different number of steps, both of those answers would be totally fine. We don't need a specific one over the other. Example 4. Again, there's multiple ways to work these, especially as the algebra gets more involved. Like when there's more steps, that means there's more ways you could go about working it. I'm just going to do one way here that's going to let me illustrate something new. 6x plus 7 equals 8x minus 17. This is given. Step 2, we're going to subtract. So we're going to do subtraction POE. Now, we could do subtraction twice. I could subtract 6x from both sides. Well, one is addition, one subtraction. So since they're adding and subtracting, we'll keep it separate. So I'm going to subtract 6x from both sides and get 7 equals 2x and minus 17. I was going to say, if you're adding more than one term, technically you could add two things at once. You could add 2x to both sides and add 7 to both sides if that were appropriate. But for simplicity and just kind of clarity, I'm just going to do this as 2 steps. So addition POE, we are going to add 17 to both sides, giving us 24 is equal to 2x. Step 4 is division. So we'll use division POE to divide by 2 and get 12 is equal to x, which feels like the end of the problem, but the prove statement said to prove x is equal to 12, not 12 is equal to x. So this is where we need the symmetric property of equality. it says that an equation is symmetric from side to side. So if an equation has symmetry, then I can flip this around and do x equals 12. And now we have our proof statement. Final example. Looks like it wrapped around to the next line. Statements, reasons. Our original equation, -7 parentheses x plus 2 plus 4x equals 6 parentheses 2x minus 4. This is our given information. Our first operation is going to be to distribute. In this case, we can't just divide by what's in front of parentheses, so we have to use distribution first. Now, I could do distribution in two different steps. I could distribute the -7 and then distribute the 6, and that would be the clearest way to do it. So I'd put -7x minus 14 plus 4x equals 6 times 2x minus 4. And then for step 3, since I'm repeating the exact same reason, I'm just going to put a quote mark, or we call that a ditto mark. And it means that we're doing the same operation again, and we don't want to rewrite the word because we're just repeating that operation. If you, in one distribution step, distributed both things, I wouldn't count off for that either. Since there's two different things to distribute, if you want to just do both at once, it's not technically the cleanest way to do it, but go for it. Minus 14 plus 4x. And now we'll distribute this side and get 12x minus 24. Step 4. So step 4, this is our first time seeing like terms on the same side of the equation. We have a -7x and a plus 4x on the left. So we're going to use the reason simplify in order to combine like terms. If you wrote combine like terms instead of simplify, I would not count off for that. That's totally fine. But we're just going to put simplify. -3x minus 14 is now equal to 12x minus 24. Step 5. Now we're going to do the kind of steps we did before. So we're going to add. So this time, just to model it differently, I'm going to do both additions at once. Again, you could use ditto marks to do it in 2 steps, but I'm going to add. So if we had -3x minus 14 equals 12x minus 24, then what I would do if I were working this problem is I would add 3x, and then since I was also needing the constant to go away from the right side, I would also add 24. So the addition property of equality just says we add the same thing on both sides. So if that thing is 3x plus 24, then no big deal. We can add 3x plus 24 to both sides. That gives me 10 is now equal to 15x. And then I need to divide. So I have division POE. That gives me 10 over 15 equals x, but I'm going to simplify that to 2/3 equals x. So in the process of dividing it, I'm also going to simplify that fraction. And then since that's not my proof statement, I need one more, which is to flip it. And remember that in order to reverse that, we use the symmetric POE. And that lets us flip the left and right side. So that's a quick tour through how we do 2-column proofs and why we start with algebra, because they're really simple. You're welcome also, like I was doing, to work the steps off to the side, and then just remember that the operations show up on the right side, and the rewritten equation at each step shows up on the left side. So there we go.